Top 10 Machine Learning Engineer Interview Questions and Answers. Machine learning engineers are in high demand as organizations increasingly rely on data-driven decision-making. The role requires a blend of programming, statistical, and domain expertise. Preparing for a machine learning engineer interview involves understanding both theoretical concepts and practical applications. Below are the top 10 interview questions, each explained in detail to help you grasp the nuances and prepare effectively. These questions cover a range of topics, from foundational knowledge to advanced techniques, ensuring a comprehensive understanding of what it takes to excel in this role. 1. What is the difference between supervised and unsupervised learning? Supervised learning involves training a model on labeled data, where the input data is paired with the correct output. The model learns to map inputs to outputs, making predictions based on this training. Common algorithms include linear regression, logistic regression, and support vector machines. Unsupervised learning, on the other hand, deals with unlabeled data. The model identifies patterns or structures within the data without explicit guidance. Clustering and dimensionality reduction are typical unsupervised tasks, with algorithms like k-means and principal component analysis, PCA. The key difference lies in the presence or absence of labeled data, which dictates the learning approach and the type of insights derived. 2. How do you handle missing or incomplete data in a dataset? Handling missing data is crucial for building robust machine learning models. Common strategies include removing rows or columns with missing values, imputing missing data using statistical methods like mean, median, or mode, or using advanced techniques like k-nearest neighbors, KNN, imputation. Another approach is to use algorithms that support missing values natively, such as XGBoost. The choice of method depends on the nature and extent of missing data. For example, removing data may be suitable if the missing values are minimal, but imputation is preferred for larger datasets to retain valuable information. Proper handling ensures the model's accuracy and generalizability. 3. What is overfitting, and how can you prevent it? Overfitting occurs when a model learns the training data too well, capturing noise and outliers, which harms its performance on unseen data. This is often due to excessive complexity or insufficient training data. To prevent overfitting, techniques like cross-validation, regularization, e.g., L1 per liter 2 regularization, and pruning in decision trees can be employed. Additionally, increasing the dataset size, simplifying the model, or using dropout in neural networks can help. Early stopping, where training halts once validation performance plateaus, is another effective strategy. Balancing model complexity and generalization is key to avoiding overfitting. 4. Explain the bias-variance trade-off. The bias-variance trade-off is a fundamental concept in machine learning. Bias refers to errors due to overly simplistic assumptions in the learning algorithm, leading to underfitting. Variance, on the other hand, results from excessive model complexity, causing overfitting. A high bias model may miss relevant relations between features and target outputs, while a high variance model captures noise as if it were a signal. The goal is to find a balance where both bias and variance are minimized, ensuring the model generalizes well to new data. Techniques like regularization and ensemble methods help achieve this balance. 5. What are the key steps in a machine learning project? A machine learning project typically involves several key steps: problem definition, data collection, data preprocessing, model selection, training, evaluation, and deployment. Problem definition involves understanding the business objective and framing it as a machine learning task. Data collection gathers relevant datasets, while preprocessing cleans and transforms the data for analysis. Model selection involves choosing appropriate algorithms based on the problem type. Training involves fitting the model to the data, and evaluation assesses its performance using metrics like accuracy or F1 score. Finally, deployment integrates the model into production systems for real-world use. 6. How do you evaluate the performance of a machine learning model? Model evaluation is critical to ensure its effectiveness. Common metrics include accuracy, precision, recall, F1 score, and ROCAUC, depending on the problem type. For classification tasks, precision measures the proportion of true positives among predicted positives, while recall assesses the model's ability to identify all relevant instances. The F1 score balances precision and recall, providing a single metric for evaluation. ROCAUC evaluates the model's performance across different thresholds. For regression tasks, metrics like mean squared error, MSE, and R-squared are used. Cross-validation ensures the evaluation is robust and not dependent on a single dataset split. 7. What is cross-validation, and why is it important? Cross-validation is a technique used to assess the generalizability of a machine learning model. It involves partitioning the data into multiple subsets, training the model on some subsets, and validating it on the remaining ones. The most common method is k-fold cross-validation, where the data is divided into k subsets, and the process is repeated k times, each time using a different subset for validation. This approach provides a more reliable estimate of model performance than a single train test split, as it reduces the risk of overfitting and ensures the model performs well on unseen data. 8. What are ensemble methods, and how do they work? Ensemble methods combine multiple models to improve predictive performance. Techniques like bagging, boosting, and stacking are commonly used. Bagging, exemplified by random forests, trains multiple models independently on different subsets of the data and averages their predictions. Boosting, as seen in AdaBoost and gradient boosting, sequentially trains models, with each new model focusing on the errors of the previous ones. Stacking combines predictions from multiple models using a metamodel. Ensemble methods reduce variance, bias, and the risk of overfitting, often resulting in more accurate and robust predictions than individual models. 9. How do you handle imbalanced datasets? Imbalanced datasets, where one class significantly outnumbers the other, pose challenges for machine learning models. Techniques to address this include resampling methods like oversampling the minority class or undersampling the majority class. Advanced methods like SMOTE generate synthetic samples for the minority class. Algorithmic approaches include using class-weighted models, where the algorithm penalizes misclassifications of the minority class more heavily. Evaluation metrics like precision recall curves and F1 scores are more appropriate than accuracy for imbalanced datasets. Proper handling ensures the model does not bias predictions toward the majority class. 10. What is the role of feature engineering in machine learning? Feature engineering involves creating new features or transforming existing ones to improve model performance. It includes techniques like scaling, normalization, encoding categorical variables, and creating interaction features. Good feature engineering can significantly enhance a model's predictive power by highlighting relevant patterns in the data. For example, converting text data into numerical representations using TF-IDF or word embeddings enables text-based models to perform effectively. Domain knowledge plays a crucial role in identifying meaningful features. While automated tools like feature selection algorithms can help, human intuition and expertise often drive the most impactful feature engineering. Preparing for a machine learning engineer interview requires a deep understanding of both theoretical concepts and practical applications. The questions discussed above cover a wide range of topics, from foundational principles like supervised versus unsupervised learning to advanced techniques like ensemble methods and feature engineering. By mastering these concepts and practicing their application, you can confidently tackle interview challenges and demonstrate your expertise in machine learning. Remember, the key to success lies in balancing technical knowledge with problem-solving skills and a clear understanding of real-world applications.